Welcome friends, welcome you all in my channel Chemistry the Mystery of Molecules. I am Tanmay. So today I shall discuss an important topic which is named as SN2 reaction on alpha haloketone. Means why SN2 reaction on alpha haloketone is faster. I shall explain that. Okay. So let's start. For this discussion I have chosen an example. That example is N-propyl chloride is reacted in presence of acetone with potassium iodide to produce this iodo derivative. Okay, so here nucleophile is I minus. Okay, react, and another thing, Ki is soluble in acetone. That is the reason for choosing this. And we have compared this with alpha chloroacetone. Here also the nucleophile is I minus and the reaction happens and produces potassium chloride and this iodo derivative. This is the new substitution. So interesting fact about this observation is that if we consider the rate of this reaction is 1, then the rate of this reaction is 35,000. It's tremendously high, at 35,000 times more reactive than this. Okay, get it? So let's start. Why this thing happens? In this case, how this reaction happens? This, for example, C3H7I. If we consider, okay, let's better. We consider CH2, C2H5I, Cl, then I minus attacks, this I minus attacks from the back side, this leaves and produces the final product. This is the main thing. Then this is happening here. Why this is so active? So this is the thing. So let's discuss. First of all, we need to know that why this is facile. Then we need to understand about the MO diagram. This is the most important thing. MO is molecular orbital theory. So this is the carbonyl and this is the Cl. Okay, this is. And another thing, we know that carbon is electron withdrawing. That's why this become delta positive, this become delta negative, this became delta negative. Okay, and another thing, due to the presence of chloride, this also became electron deficient. So this bond, this methyl group doesn't donate enough to the carbonyl. Okay, so then if we draw the MO, but before going to that, let me give you some about the pi and pi star. So if a double bond is formed, for example, carbon and oxygen, this is a pi bond, and this looks like this, plus and minus. If this is pi star, this looks like this. Okay, this is plus, minus, minus, plus, minus, plus, plus, minus. Okay, so this looks like this. This is pi, this is pi star. And if we consider the sigma is sigma between C and X. This is a sp3 overlap. This forms this sigma having 2 electron, and this is the sigma star, which is this having no electron. This pi star having 2 electron, this having no electron. This is a pi star. Okay, no electron. So this is. So what happens? Nucleophile is attacking to the pi star. That's why this bond is breaking. I have explained this in case of SN2. So please have this. You have a better idea. So right now these two orbitals are overlapping. Okay, here plus minus overlapping. How? This is the pi star. Just I have drawn try to understand. Plus minus plus minus. Okay, and this is the sigma star. Okay, so this is plus minus plus minus. This is, and right now, if you consider, so now the reaction happens. If you consider valence band approach, then you can conclude that this CO is electron withdrawing. That's why the pentagonal by-pyramidal intermediate followed during the SN2 reaction, like, what do I mean? This is CH3 and both 2 are H. This is pentagonal by-pyramidal. This is the Cl and this is the iodide. Okay, this is the TS having negatively charged. So this is SN2. This p-orbital contains 4 electrons. Okay, so this is due to the electron withdrawing. This electron density is a more electron rich because this is a 3C4E bond. More electron, that electron density is dragged due to the withdrawing effect of oxygen. It's true. From valence band approach, it is true, but we can say we can have a better explanation if we consider from MO explanation. Okay, and now this part you got. Now I'll explain about the MO. What happens in case of MO? This pi star and this sigma star overlap. How you have to observe this zone. This zone. Then you can understand this. Here, these two can overlap. What happens? This sigma star and pi star. If we overlap this pi star and sigma star will be relatively higher in energy. Then they will overlap to form two new other molecular orbital because they are molecular orbital. They are overlapping to produce new. This is sigma star has no electron, pi star also has no electron, but here the twist. Now the new LUMO, this is the LUMO, newly formed. Okay, so let me clean. This newly formed LUMO is lower in energy. And if we compare about this propyl chloride, there, this is the LUMO, sigma star. So right now this LUMO is lower in energy, so electron donation is favored compared to the LUMO in case of propyl. So two factors, one is withdrawing and one is this combination, this LUMO, and here nucleophile means here iodide and ion gives electron, lower in energy. So here the energy of activation is lower for this attack. This is the first, and second you can explain from VBT approach due to the withdrawing nature of this, how this p orbital is in same conjugation with this, means it is not looking in the same plane. If you draw properly, this donates its electron to the pi star. There is a chance that this excess electron density could be distributed. So this is the MO theory approach and this is the VBT approach, valence band theory. Then you can explain why this shows enhanced reactivity compared to this, and this is the uniqueness of alpha halo star as for SN2 reaction. But is it a common for SN1? For SN1 reaction, this alpha halo carbonyl compound is very unreactive. This is some extra example I am giving you. Why? SN1 reaction means the formation of this carbo-cation here, which is highly stable due to the withdrawing effect of this carbonyl, and that's why it is not stable compared to this. This is an allylic system, because in allylic system it can have a resonance very efficiently, means charge would be delocalized with the equivalent canonical structure. So here this is fast, this is faster. So alpha halo-ketone undergo SN2 very efficiently, but not SN1. But in case of allylic system, SN1 is also possible, SN2 is also possible. Please keep, because it can have also a canonical form with this. Okay, so this is the strategy to understand the fact. So I guess you have understood the fact, and please keep it in mind, it is important. So finally, if you like my teaching, please give some thumbs up and share this video among your friends such that many people could get benefited from my effort. And finally, subscribe my channel Chemistry and History of Molecules, and please press the bell icon to get the notification of every single video I upload. So see you in my next video. Bye.